Let's move on to digital. So two types of digital recording exist. The stationary head, which is the same, and when I'm talking about digital tape, not Pro Tools. They had digital tape machines before we went to Pro Tools. There was the stationary head, and there was the rotating head. Rotating head is something you'd see in something like a VCR. People don't remember what a VCR is, do they? A VCR used to be a cassette. It would record in a digital format, it would record video. So the head would rotate and the tape would move very slowly, and the head to tape speed difference created the same situation that if the tape was moving fast across a stationary head. The whole object is that you wanted the tape to move quickly across the head to get the quality that we're looking for. That's why 30 inches per second was better quality than 7.5 inches per second, because the tape was moving quicker. They came up with all sorts of alternatives. The rotating head was great because you didn't have to use a lot of tape. The head was moving, so it was a quick head-to-tape speed. The DAT players used a rotating head. DAT was a digital audio tape machine. So let's talk about the recording process for digital. Basic signal flow looks to be the same as what you'd have in the analog domain, where you've got a sound field, acoustic energy is turned into electrical, it's manipulated, it's stored, it's manipulated again, it's transduced, and then it's played back to analog to an air disturbance. Digital is quite a bit different than analog recording. The audio signal, the map of the amplitude over time, is represented as a string of numbers instead of a continuous voltage that fluctuates. Converted to a digital signal by sampling, we'll talk about what sampling is, and the waveform is no longer strictly proportional to the original waveform. So what you've done now is in some way we've created a process, and I'll explain the process, where we take an analog signal, which is fluctuation in voltage, and we've somehow coded it into numbers so that you could take that code and decode it and get back to a voltage fluctuation, which could then go into a speaker, which makes the speaker move and create the air disturbance again in the same way that it was recorded. So we're doing some sort of a coding in the digital domain. Let me give you a little overview as to sort of the thought process behind the people that designed and basically developed the digital kind of recording techniques. At least this is how I think about it. I think of audio very similar to visual arts. And I don't know if anybody's familiar with pointillism, which was a technique of the Impressionists, artists, where they would take different colors of paint and they'd dab little dots on a canvas rather than making a continuous stroke. They would just put little dots, little dots, little dots, and then you stand back and all of a sudden you start seeing a picture out of these dots of color. When you stand very close to the painting, it looks like a bunch of colored dots. It doesn't look like a picture until you stand back and you go, wow, it's a picture. Very similar to what halftoning is in newsprint, where they have like a bubble jet printer, spits out little dots, and the more intense the dots are, the more dark the area is, the less intense, the more gray tone it has. So if you think about that, what they're doing is they're taking a continuous surface and they're breaking it up into small little component pieces and then building a picture out of that. And when you step back, your eyes blur this all together to being continuous again. So the thought process is that if you take an analog signal, which is a continual voltage fluctuation with no breaks, and you would take samples of this at various time intervals, very quick samples, and you'd get a voltage at where that signal was at that one little glimpse of the sample, and then you take that where that voltage is and you assign a digital number to it. Then you can actually code how the signal was moving, and then later you can decode it. In digital recording, the amplitude domain is quantized, meaning that there's discrete levels of voltages that it'll allow it to be at or that it'll read it at and conform it to. The digital signal is derived from the analog signal and must be reconstituted as an analog signal before it can be reconverted back to sound. Let's go through a few little terms and then I'll get more detailed about how that process of coding it works. Okay, so digital terms. A bit is a single piece of data, a 1 or a 0. A byte is an 8-bit word, so it's got 8 single zeros or ones. Kilobyte, I give you all of this information, which is kind of interesting. A megabyte tells you how many bytes are in a megabyte. A word is a block of binary data, and a few other terms. One thing that I know that people generally don't think about is, why is it that computers are called digital? Digital meaning binary devices. And why is it just a 0 and a 1 that computers operate in that machine language? Has anybody ever thought about this? It's exactly true. The light is on or it's off. Two discrete states, 0 or 1. Your computer, actually your microprocessor that runs your computer, you know, that chip with hundreds of legs coming out of it, and in your phone the same thing, that's thousands upon millions of little switches, and they're either on or off. On is a 1, off is a 0. The computer can actually understand ons and offs, and it gets assigned to zeros and ones, so the computer essentially thinks in base 2 mathematics. Does anybody remember this from way back when you talk about base 10? Like, why do we count in base 10? Because we've got 10 fingers. 1, 2, 3, 4, right? I'll give you a really short synopsis on this. It's actually interesting. This is actually interesting for everybody to know who has any sort of digital device. Okay, base 10, mathematics, right? So you've got your columns for your numbers. You've got a decimal point. This is the tenths column. This is the hundredths column, right? Everybody knows that, right? This is the ones column, tens column, hundreds column. So when we write a number, 101 means, oh, we need 1 100, 0 tens, 101 is 101. Means you take the number in the hundreds column, add it to the tens, add it to the ones, and you get your number, 101. And in each column, you have the opportunity to put any number between 0 and 9. The ones column can be 0 to 9. If it's 10, you got to jump to the next column and put a 1 in the next column. That's basic base 10 mathematics. Now, the computer can't think in base 10 because there's not 10 discrete states in the computer. There's only 2. So, computer operates in base 2. Let's talk about that. You've got your columns again. But in each column, you can put a number between 0 and 1, because that's the 2 states you have. So let's say, so you've got the ones column, you've got the twos column, you've got the fours column, and the eights column. Let's say we wanted to write the number 13 in base 10 would be 110 and 3 ones. In base 2, how would we write that? 18, 14, that's 12, and 11. That's base 2. This represents 13 in base 2. This represents 13 in base 10. The point is that the larger the number, the more digits you need in the digital world. And that's why these processors are feverishly processing is at the speed of light to accomplish what we're trying to accomplish. So already you can see how marvelous your computer is, right? Just to do some very simple functions, it's got to manipulate and throw these ones and zeros all over the place. In base 10, it's much more efficient. We can write 3 digits that takes lots of digits in the base 2 world. So my contention is eventually what will happen is that Intel will come up with some sort of processor that has 3 discrete states. And then you have base 3 to work with. Then your words can be shorter, less data to store, less data to manipulate. As you know, computers are getting faster and faster and faster and faster till they can't get any faster because they're working as fast as the speed of light. And so you have multiple processors in parallel processing. And so that's the i4 or the i8 chip where it's got 8 processors in parallel. And you've got all this fancy stuff to get work done faster. Because in a linear fashion, it can only go at the speed of light, and there's so many switches to move around. So, but in base 3, it would be 100 times more efficient. In base 10, it would be like our brains. So eventually, if electronics could come up with 3 discrete states, like off, halfway on, and fully on, then we'd be able to go to base 3 with the processors, and everything, the whole dynamic of computers would change. Everyone's experimenting with this stuff, and I'm not hip on the latest technologies of that, but I can't wait till they get to the point where, they can think, computers can think like we do in base 10. It'd be amazing. It'd be much faster to compute.